Hello friends, we start with our next topic. I think you have gone through my previous video in which we have already talked about Thevenin's theorem and Norton's theorem. Okay, so our next topic is maximum power transfer theorem, which is very most important theorem, and there are a lot of problems you will find in various competitive examination. Before going for our topic, if you have still not subscribed, share and like my channel, please subscribe it, please share it. Once you subscribe, it will be more easy for you to go through my all video in a sequential manner and one can easily able to understand this subject. Okay, so we start with our next topic known as maximum power transfer theorem. Now we are talking about maximum power transfer theorem. You will find there are a lot of different type of question used to come in examinations. So we will see how we'll understand the concept of maximum power transfer theorem. So first of all, we will see, let us consider a network having a terminal A and B. Now please try to understand the basic concept. And for the time being, yes, it is a variable load resistance. You will see when you go through your communication network subject, there is one subject known as communication networks, in which you will see this term will use somewhere, like in antenna also, in various communication networks also, in even in your semiconductors area also, you will find there would be a concept of maximum power transfer. There are conditions in a network in which sometimes there is a requirement of transfer of maximum power from this network to the load which is further connected at its terminal. Okay, once again I am repeating, there are certain conditions arises or sometime it is required in the network in which a maximum power transfer is required from a certain network to the load which is connected to its terminal. So actually the point is you have to find that condition under which this network will deliver maximum power to this load resistance. Okay, you have to find the condition of this network so that this network will deliver the maximum power to the load which is connected here. So basically you can say that you have to find a certain condition in the network where the maximum power transfers occur. So now the very basic question is how we find that condition. Okay, how we find that condition under which a maximum power transfer from some network to the load. So for analyzing such type of condition, what we will consider, we draw equivalent of this network. Very important thing, please keep in mind. We'll draw equivalent of this network, and this equivalent is basically Thevenin's equivalent. Is what? It is Thevenin's equivalent. So if I draw Thevenin's equivalent of this network, please see. So you can say this is your VTH, this is your RTH, this is your VTH, and here is your terminal. And now you see some load that we call it as RL is connected. So what I did, I just replaced this network, this entire network with this equivalent combination. Okay, and here at this terminal your load is connected as it is as RL. Okay, so if you have to find the maximum power transfer across this load with the help of this network, so basically you have to find the power across the load resistance, or you can say the power across your load which is connected across terminal AB. So Can you able to find that power? Yes. Yes. If I say there exists some power P, so what is that power? That power either it is I square into RL, or you can say V square by RL. But for the time being, I will consider this as our power across the load RL. So basically you have to find the value of current I here. You have to find the value of current I here. Okay. So you just apply one KVL. So you can say VTH is equal to I into RL plus of RTH. Yes, you can say, or you can say the value of I is what, that is VTH upon RL plus of RTH. This is your value of current I. Yes, you can say the value of current I is what, that is the sum of load resistance and Thevenin's resistance, and when you divide by this voltage, the current which is flowing in this network. So if I go for finding out the power for this network, the power formula comes to be, as I said, I square into RL. The power, this is a power across load, very important. And what is your load? Your load is RL. So you can say the value of power comes to be, the value of I comes to be what? That is VTH upon RTH plus of RL whole square into RL. Yes. So this is your power across the load. This I can say power across load. Okay. But when you talk about the condition of maximum power, which, as I said earlier, sometimes require a network to be transferred from one network to the load, you have to find the condition of maximum power transfer. Okay, you have to basically find the condition of maximum power transfer. So as you studied in your mathematical portion, if you have to find the maximum of certain quantity, simply you have to make a differential of that particular quantity. So since I have to find the maximum power, I said this P will become P max. This P will become P max under the condition when dP upon dRL goes to 0. Should I say, if dP upon dRL goes to 0, so this is a condition at which you can find the maximum power in the network. So now basically you have to find the value of dP by dRL. It means you have to just differentiate this entire value, and you have to find the value of dP upon dRL. Okay. So what we'll do, we'll find this dP by dRL. So you have to just differentiate this value. You have to just differentiate this value. So if I write here dP upon dRL, so that should be equal to d upon dRL. That is your term VTH square upon RTH plus RL whole square into RL. Okay, and that should be equal to 0. Well, basically you have to find this differentiation, and once you make it as 0, you will find the condition. So see, I am not going to solve this value because you can easily able to solve this, and one can easily able to find that answer. What we will consider here, we will mainly interested in finding out the condition. So when you are going to solve this, I will directly write the condition which we able to obtain here. That condition is, when you solve this, just a very simple differentiation. So under this condition, when you solve this, the value of RL comes to be RTH. just by solving this, you'll get this value. So the value of RL comes to be RTH. Very important thing. So this is a condition. When this condition is applicable in this network, so the power will get maximum. Now your question is, what is that maximum power? So now we'll see what is that maximum power. So if I talk about that power, that is P max, which I have already mentioned you, that is P. First of all, we'll write the power P. That power was what? It is V square TH into RL upon RL plus RTH whole square. Okay. Now if you put the value of RL or RTH, so that comes to be VTH square into RL upon what it is, the value of RL as RTH. So what I am doing here, instead of RL I am writing here as RTH, because we have to find the condition for load. So here it will become twice of RTH whole square, and that comes to be 4 of RTH, and finally you can say it is VTH square upon 4 of RTH. So this power will now become your maximum power when you put this condition here. Okay, this is a very important formula for finding out the maximum power in a network. So now 2-3 things we understand here. Whenever you have to find a maximum power, first you have to find the value of RTH. Okay, then you have to find the value of VTH, and then you have to find the value of Pmax with this formula. Okay, now in GATE sometimes they used to ask about, not sometimes, in most of the questions they used to find the condition of RTH. This is a common type of problem used to come in GATE with different type of circuits, and in a rare condition they used to talk about Pmax. Why? Because while you are finding Pmax you have to find VTH also, and generally that question is of 2 marks. So you can say when you are finding RTH it is a 1 mark question, and when you are going to find Pmax it is a 2 mark question. Okay, this is 1 marks and this is 2 marks question. And believe me, the questions are very easy. Only you have to simply apply the concept of KCL, KVL, okay, and then the concept of theorem, which we have already discussed for Thevenins and Nortons also. So simply you have to apply the concept of Thevenins and one can find the value of RTH. We will see in different problems how the condition of RTH vary in these type of networks. That we will see, because that is an important part. And finally, once you know the value of RTH and VTH, you can easily find the value of maximum power, that is Pmax. Okay, so this is all about the maximum power transfer. Now we will discuss one graph. And that graph is basically the relation between power and load resistance RL. Okay, so if I draw that graph, so actually please see, this is the relation between power and load in a network when we are talking about the maximum power transfer. This is a general relationship. This is your power in this axis, we call it as y-axis. This is your x-axis, where is the load resistance RL. What we are analyzing when the value of RL is varying continuously. As I said, this RL is what? Basically a varying load resistance. RL is what? It is a basic varying load resistance. So when you are changing the value of RL from 0 to say some value here, okay, 0 to some value, say that is an x. So what happens? You will find when you are increasing that value, a point reached at which when RL and RTH becomes equal, it was analyzed that the graph in the circuit will become like that, and there is a peak in the graph. and you know here the slope of your tangent will become 0, and you call that point is a point at which maximum conditions occur. So that's why I have taken dp upon drl as 0 because of this condition. So once you find dp upon drl, so one can able to find the condition of load. Okay, and that's why we came to know that when RL become equal to Thevenin's resistance, the graph will move in this fashion, and this is your maximum point, and the power which we got here is a maximum power. So once again, you'll see when you are increasing your load resistance from 0 to the value of Thevenin's resistance RTH, you will find the power slowly increase in the circuit. Yes, this is an increment sign. But once that maximum achieved, that is when RL will become RTH, now your power starts decreasing. Okay, so you understand, from 0 to RL, the power starts increasing, and once a peak reaches, that is at Thevenin's will become equal, that is load will become equal to Thevenin's resistance, your power will decrease in this manner. So this graph is very important. Sometimes ticklish questions or a descriptive type of question used to ask from this graph. So once you know about this graph, you can easily able to answer it. Okay, so this is all about the maximum power transfer theorem. We will see its AC application. Okay, since it is in we are talking about right now about the DC circuits, we will see the application of maximum power transfer in AC circuits also, and there we will discuss about the concepts of maximum power transfer, how it is applicable in AC circuits. Okay, because you will say there are certain problems which were asked in GATE from AC point of view through maximum power transfer theorem. Okay, so that we will find out in AC topic. So as of now we are talking about the DC, and the DC we have seen how we have find the maximum power, and finally one can able to understand this graph. Okay, now we go for the next concept, and please keep in mind one more important thing. As I said you here, when RL is equal to RTH, one more important thing, when RL is equal to RTH, then only you can find the maximum power, as we have already seen. And once RL is not equal to RTH, it is simply, you can say it is a power P, not maximum. Okay, not maximum in nature. Okay, so this is all about maximum power transfer theorem. Now friends, we start with our next topic. I would not say it is a topic, it is a type of concept. You will find various time this concept used in GATE, and they used to generally ask a problem in under this topic. Okay, so we will see. I already explained you about the Wheatstone bridge in my previous videos, and you know, you will go through when your semester subjects, you will find that what is the concept of Wheatstone bridge. You know about the Wheatstone bridge, there is a condition known as P upon Q is equal to R upon S, where P, Q, R, S are the resistance. So you call, when this condition is applicable, the bridge is balanced. What do you call? The bridge is balanced. It is simply like this. Okay, this you call it as P, this Q, this R, and this is S. Or simply you can say when PS is equal to RQ, you call it as the bridge is balanced. The very important thing is, when bridge is balanced, what should be the condition? And when bridge is unbalanced, what should be the condition? Okay, so I have already solved a few problems in my problem solving sessions. In my previous video, you may go through that. So if this is a galvanometer, here the galvanometer is connected. Okay, see, when this galvanometer is connected here, and sometimes you have to ask, sometimes the question will come, they will ask about the value of current flowing here. The value of current flowing here. This is a common question used to come in GATE and another examination. They asked, when galvanometer is connected in this manner, what is the value of current I. Now first we will see the condition of balanced bridge, and then we will see the condition of unbalanced bridge. Bridge means this is your bridge, this is your bridge, okay, and basically it is what? It is a Wheatstone bridge. What we call it as Wheatstone bridge, okay. So this is a kind of Wheatstone bridge where these two terminals are known as AB, and a galvanometer is connected between these two terminals just to identify what is the current flowing through the galvanometer. Such type of question generally used to come and they will ask this problem. Now first of all you have to analyze whether the bridge is balanced or not. So simply you see this condition. If this condition exists here, that means the very important thing, if it is a balance in nature, that means VA and VB, when the bridge is balanced, it means no current will flow from here. Just write. First condition, when bridge is balanced. This is very important thing. Just focus. When bridge is balanced, the very important thing is VA, the voltage across the node A, and the voltage across the node B will become equal. Very important thing. That means no current flow through G, that is galvanometer. Very important thing. Okay. So under this condition, what is the nature of the problem? They just ask you, either you have to find, sometimes they say if this terminal is open and you have to find the potential difference. Okay, when this galvanometer is connected and when no current is flowing here, so they just used to ask what is the potential difference. That is an open circuit potential difference at these two nodes. So how you can find? This is only possible by finding the value at VA and the value at VB. So just keep in mind, when such type of condition exists, that is your bridge is balanced. So under this condition, simply you have to find the value of VA and VB. And how you find the value of VA and VB? Now VA and VB, how you find? Please see. VA is the potential across R2 resistance and VB is the potential across R4 resistance. So one can easily find the value of VA and VB. Okay. So the value of VA, how we are finding it is because this is an no current flow. It means this is an open. No current flow. It means this is an open terminal. And since it is an open terminal, you can find the potential difference between these two terminals. And for finding out the potential difference between these two terminals, one can find the value of VA and VB. And finding out the VA and VB is a very easiest thing, just to find VA by using voltage division rule. So that comes to be R2, because we have to find across this resistance. So it is R2 upon R1 plus of R2 into your actual voltage which is applied. This is the voltage. Okay. Similarly, the value of VB comes to be what? That comes to be the voltage across R4 resistance. So you can say it is R4 upon R3 plus of R4 into V. So this is your VA, this is your VB, and with the help of V and VB, one can easily able to find the value of potential difference across these two nodes. This questions used to come. So you can say that what is the difference between these two nodes? I can say it is V equal to what? It is the difference of VA minus VB. Yes? You can say it is VAB. You can also say that it is what? It is VA minus of VB. And we have find VA minus VB with the help of VA and VB. Okay. So this is all about the concept of galvanometer. We will see in our question session especially. Here you just try to understand the concept. So this is all about the condition when bridge is balanced. Now the very important thing, when bridge is unbalanced, what will happen? Okay. Now friends, this is your next condition. First we have discussed about the balance. Now we have discussed about the unbalanced bridge condition. Unbalanced bridge condition, it means you can say that R1 upon R2 is not equal to R3 upon Rx. Very important thing. In my previous video, I think I have not written that value. There R1 upon R2 was equal to R3 upon R4. Okay, this condition for balance and this condition for unbalance. Okay, so since we are talking about the unbalanced condition, just you keep in your mind, we'll talk about the unbalanced condition. So this is your condition. Here I have introduced one more resistance known as Rm, which is resistance of galvanometer. This galvanometer. So you can say it is an internal resistance of galvanometer and we call it as Rm. Now again, in gate itself you will find a question used to come. You have to find the value of I here. This is generally a 2-mark question and you have to find the value of current I in this branch, that is AB. Or basically you can say the question used to ask, you have to find the value of I flowing through the galvanometer G, okay, with the internal resistance as Rm. So now the question comes to how we find that the value of I in this case. Okay, so this is a new type of problem in which we have to find the value of I in this case. So just keep in mind what we will do. We will find the Thevenin's equivalent at these terminals, or you can say at terminal AB. I am drawing here. Say this is our 2 nodes we will consider and we call it as AB. Again the same node. Okay, so what we will do, we will find the Thevenin's terminal at AB, and once you know the Thevenin's equivalent at AB, so what is that equivalent? So that comes to be what? Say this is your VTH. Say this is your VTH. This is your RTH which you have find, and this is the terminal and this is Rm. So once you find this value, you can say this is the value of current which is flowing through this galvanometer. Okay, so can you say that the value of I is VTH upon RTH plus of Rm? Yes, very easy. Very easy, you can find the value of I, and your I is what? VTH upon Rm plus RTH plus Rm. So now, okay, so you have to find the value of VTH and RTH here. So how you find the value of VTH and RTH? So you have to just apply the same concept which we have discussed earlier in case of when the bridge was balanced. See, in that case, the only thing that the bridge was balanced and because of that no current was flowing here. But in this condition, some current is flowing here. So what we applied, what we have done, we have just find the Thevenin's equivalent across this terminal. And with the help of this VTH and RTH and the resistance which we know about Rm, simply we have find the value of current I. So finding out the value of Thevenin's resistance is basically what? It is VTH. You can say this VTH is what? Is the difference of these 2 voltage. Yes? This VTH is what? This VTH is what? Because when you are going to find the VTH here, that is your open circuit here. So basically you can say you have to find this A or you have to find this B. Once you know this voltage VA and VB, the difference of that voltage is what? Your VTH. Yes? So in this manner you can find the value of VTH. Now the question comes to be how you find the value of RTH. So RTH is what you have to find here. At this branch you have to find RTH by short circuiting this branch. So if I draw the equivalent of this network, please see, if I draw the equivalent of this network, so this terminal will become open, this will become short. So actually this is this type of network. So when this is short circuited, why? Because this voltage source gets short circuited. So you can say that the value of RTH is what? It is these two resistance comes into parallel, these two resistance comes into parallel. So you can say R1 parallel R2 plus of R3 parallel Rx. So with this you can find the value of RTH. So you have find the value of VTH, you have find the value of RTH just by putting this value here, because you know the value of RM, one can find the value of I. Okay, one can easily find the value of current I in such type of network. So we have studied about two type of condition, balance and unbalanced. It means when the bridge is balanced and when the bridge is unbalanced. So when the bridge is balanced, so very simple, you have to find the value of V and VB. There you have to not apply any VTH. Okay, I have not talked about any Thevenin's equivalent there. But when we talk about the bridge is unbalanced, in that condition what we will do, we will make these two terminal, we will find the Thevenin's and Thevenin's equivalent across these terminal. As I said, it is a type of complex network where it is difficult to find the current I. So what we will do, we will find the Thevenin equivalent across these terminal AB. And once finding the Thevenin's equivalent across terminal AB, you can easily get the value of current I. And how we get VTH and RTH, that I have already mentioned. This is your VTH, the voltage difference between V and VB, and this is your RTH. This is the formula. Okay. So this is all about the resistance measurement, and you will see the problem used to come from this topic. Okay.